Thanks, me from the past. I'll take over from here. So the last thing I want to talk about today is big O notation. It's closely related to big theta. So as you guys know from what you just saw, big theta is used to describe the order of growth of a function. And we also use big theta to describe the rate of growth of the runtime of a piece of code, like dup2 or dup1. So big O is an alternate idea, which whereas if you think of big theta as equals, you can think of big O as less than or equal. So for example, the following are true. This function, n cubed plus 3n to the fourth, is big theta n to the fourth. Its runtime, its order of growth is n to the fourth. It is also less than or equal to n to the fourth. It is also less than or equal to n to the sixth, or n factorial, or n to the n factorial, because all of these functions grow no more quickly than n to the fourth. Okay? So whereas formally, big theta says that our function can be sandwiched between a smaller version of f and a larger version of f in order to be big theta f, for big O, we just omit that lower bound. So we say that it's smaller than some scaled up version of the function f. Okay? So for example, if we look at a visualization here, let's consider this function 4n squared plus 40 sine n. Okay, so this is in red, I have here the actual function r of n, and we see that at first it is bigger than my upper bound, but eventually for a large enough n, it is smaller, right? So all I'm saying there is, look, this function grows more slowly than n to the fourth. All right, so that's it for big O. It's really not that different. Okay, so example on the slides, basically what we just saw in our example, and there you have it. Okay, so to contrast big theta and big O, you can think of n squared, the function n squared. If we say theta n squared, there's a whole family of functions that all grow at that order of growth, like n squared, 2n squared, n squared plus 38n plus n. And then big O is a much bigger family of n squared. So for example, log n, 2n squared over 2. Anything that grows at n squared or slower is big O. Now it may seem like this is just a somewhat weaker concept, but we'll see why it's practically useful in the next lecture. So to summarize everything we did today, both version of me from the past and me today, when we are given a code snippet, we can express its runtime as some function r of n, where n is some feature of the input, usually maybe like the size of the list that it's given, something like that, but it could be arbitrary. Now, rather than finding r of n exactly, which is generally impossible because it would require a very detailed model of our computer, we instead usually only care about the order of growth of r of n. And we saw an approach for actually finding that order of growth. The way we did it today, but it's not the only way, is pick a representative operation, we'll call that our cost model, and we let C of n be the count of how many times that operation occurs. We then figure out the order of growth for that operation itself, for the operation. So for example, if we say C of n, the number of times that our cost model actually occurs, if it is theta f of n, then that tells us that the order of growth here is, it grows at a certain rate, like we saw with dup. Now, often but not always, we consider the worst case count. In this lecture, it was almost all worst case counts, and that's usually what you're going to do. And if that operation, the one that we're counting, takes constant time, then the overall runtime will also be theta f of n. And then lastly, we saw that we can use big O as an alternative for big theta, and O is, we'll see later, used for upper bounds. All right, that's it for today, and I'll see you in the next lecture.